Hi everybody. This is our lecture on section 6.7 on Stokes' theorem. So let S be a smooth, continuous two-sided surface with front to back to front with oriented surface from side 1 to side 2, and whose boundary is a simple closed curve C. Where C is oriented according to the right-hand rule. Is according to the right-hand rule with respect to S. Okay, what exactly is meant by that? So here's my surface S. Like that, like so. And S is oriented from side 1 to side 2. So this is S here, sort of in that general direction. Now C is the boundary of this two-sided surface, which is supposed to be, in the case of Stokes' theorem, a simple closed curve, which has one of two possible orientations, right? One of two possible orientations. We are stating Stokes' theorem for the orientation which respects the right-hand rule. And what is meant by that is as follows, is if you take your right hand and you sort of flatten it out and you slide your fingers in the direction along C, then your thumb should match S. Right, so for this drawing here, right, I'm sliding my right hand in this direction and my thumb is pointing in that direction. Let's actually give that a draw. Alright, so I've got my fingers, 2, 3, 4. I'm sliding my fingers in that direction, and my thumb is agreeing with S, with my right hand. Okay? Okay, so according to the right-hand rule, Stokes' theorem says the following. If vector field F has continuous first partial derivatives, then the line integral along C of F dot ds. So the line integral along C. So C is that boundary. S, right, is the surface that's bounded by that boundary, is equal to the surface integral over S of the curl of f dot ds. So the line integral is the surface integral, not of the same vector field, but of the curl vector field. Okay, notice that one consequence of that is if two different surfaces have the same boundary, then their surface integrals are the same. The surface integrals of the curls are the same, the flux integral. Again, by the way, notice this is a theorem about vector surface integrals. It's not a theorem about the scalar surface integral. It's a theorem about the vector flux surface integral. So this theorem, Stokes' theorem, and in the next section, section 6.8, on the divergence theorem, are both about vector type integrals. The scalar type integrals for curves and for surfaces don't have any theorems that simplify them. They just are what they are. Okay? One consequence of this fact: if S1 and S2 have the same boundary C, then the surface integral over S1 of the curl of f dot ds is equal to the surface integral over S2 of the curl of f dot ds. Okay, because they're both equal to this. They're both equal to the line integral over C, which doesn't care what the surface is. Just that its boundary is C. Now, Stokes' theorem is actually a three-dimensional analog of Green's theorem. Is a 3D analog of Green's theorem. Because, for example, not for example, but because suppose that C and C and S are just in the xy plane. So suppose that surface S and its boundary C are in the xy plane, right, with S oriented upward and C in the counterclockwise direction. So here's our three-dimensional space, but our surface S is just down here with its boundary along with it. So this is S, and S is oriented in that direction. So S Alright, and the boundary of S is C. It's going to be going in the counterclockwise direction when you look at this guy from above. Right, just like in Green's theorem. That's what the right-hand rule gives you. You slide your fingers in this direction, which is counterclockwise, where X is going off to your right and Y is going up. So that this direction is right, this direction is up. Right? When you look at the XY plane in the usual orientation of it, right? That's the counterclockwise direction. Anyway, that's what your right hand is giving you. and your thumb is pointing upward in the z direction. Okay, so the surface is going this way. Notice that the unit normal vector in this case is just 0, 0, 1. That's the vector that's perpendicular to the surface and it has unit length. Perpendicular to the surface is just in the z direction. Oops. Right? So in this case, F is just equal to P, Q, R. And the curl of F is, remember, it's that 3 by 3 determinant. Partial with respect to x, partial with respect to y, partial with respect to z, p, q, r. So this is equal to, well, I don't care what's in the x component. I really don't care what's in the y component. The z component is qx minus py. Right? Partial of q with respect to x, partial of p with respect to y. Here, I'm not really interested. So the line integral on C of f dot ds is equal to, by Stokes' theorem, the surface integral on S of f dot ds, which is equal to its definition, or not f, I'm sorry, curl of f. Which is equal to surface integral over S. Curl of f is equal to something. Something qx minus py dot ds. Which is equal to, by the definition of the surface integral, the double integral over R, whatever region it is, of this vector field, qx minus py. Actually, let me, I don't like the way it's looking now. So, by the definition of surface flux integral, this is the curl of f vector field dot unit normal vector in dA, where a is over the dA is over the range for x and y. So this is equal to, just from what we have here, double integral over R. Curl of f is something qx minus py. Dot, the n was 0, 0, 1. That's the unit normal vector. dA, which is equal to the integral over R. Well, I mean, R is actually going to be the interior of C. Which is actually the surface S. But in this case, it's the interior of C. C is that boundary. Well, it's a dot product. I didn't care what this is because the dot product is going to be 0. The product of this and 0 is 0. The product of this and this is 0. So it's just 1 times that, which is qx minus py dA, and that is Green's theorem right there. Right? In the case that you're working just in the xy plane, right? Green's theorem gives you this. For the line integral over C, it's equal to the double integral over the interior of C of this expression here. partial of q with respect to x minus partial of p with respect to y. So here Stokes' theorem, which uses the curl, is a three-dimensional generalization or analog of Green's theorem. Okay? All right. So let's take some examples. So let's take S to be the part of the plane shown oriented upwards. So here's x, y, z. So let's look at the plane z equals, let's say 6. Let's say z equals 12 minus 3x minus 2y. So when z and y are equal to 0, we have x equal to 4. And when x and z are equal to 0, we have y equal to 6. Let's put a 4 here, so we get y equal to 3. And z equal to 12 up here. So this is our surface S right here, this plane. And we're going to orient the guy upwards. And let C be the boundary curve of this. So C is this boundary of the triangle oriented according to the right-hand rule. Like that. And then C is the boundary curve. And then C is the boundary curve. Of this surface. Now let F be equal to xy squared, x plus y squared, y plus z squared, z plus x squared. And let's use Stokes' theorem to calculate the line integral over C of f dot ds. Okay, so, one could calculate this. So one can't use Green's theorem here because this is not in the xy plane. One actually needs the full generality of Stokes' theorem. Now, of course, we could calculate this just using the definition of the line integral. Okay, but instead, let's calculate instead we will use Stokes' theorem. Okay, well, in Stokes' theorem, we need to know what the curl is, right? So the curl of f is equal to I j k partial with respect to x, partial with respect to y, partial with respect to z, x plus y squared, y plus z squared, z plus x squared. All right. So this is equal to, so partial with respect to y minus partial with respect to z, so that's just minus 2z. And then partial with respect to z minus partial with respect to x minus 2x. And then partial with respect to x minus partial with respect to y minus 2y. So that's minus 2 times z x y, like that. The surface S, right now, in order to calculate a surface integral, right, we need to parameterize the surface, right? So the surface, let's take a look at it. All right, here's that surface. Now we need to parameterize, and I'm just going to use the standard or trivial parameterization. Right, so the trivial parameterization of this surface, the region for x and y, is right here. So the region in x and y is right there. The parameterization is r of x, y is equal to, well, x is x, y is y, and z is this. Right? For xy in this region right here, so that's x out to 4, y out to 3, Alright, so that's 0 less than or equal to x less than or equal to 4, 0 less than or equal to y less than or equal to, well, the slope here is minus 3/4 x plus y-intercept c. Alright, so that's the equation, that line, minus 3/4 x plus 3, because that's the slope there. Right, rise over run is minus 3/4. And then y-intercept is 3. So that's the equation of that line right there. So that's the region over which we will eventually calculate this integral. Okay? So, remember, what are we calculating? We're calculating the line integral. Is equal, by Stokes' theorem, the double integral over S f dot ds. Okay, which is equal to, right, well, what were the other ingredients that were necessary here? Well, this is, not f, the curl of f, sorry. Curl of f dot ds. Now, what were the other ingredients that were necessary here? Which is equal to, by definition, of the vector flux integral, double integral over r, the curl of f along the parameterization rx, y, dot rx cross ry dA, right? There was that cross product, rx cross ry, because we're oriented in the upward direction, right? Rx is in this direction, ry is in that general direction. So the cross product rx and ry gives you the orientation in the upward direction, or outward direction. You like to think of it more as upward when you're talking about the surface z equals f of x, y. Ry cross rx, using your right hand, points downward. Right, so we need to calculate those as well. Maybe we'll do that here. Let me move this down, and then we'll calculate that cross product. So partial of r with respect to x is equal to 1, 0, minus 3. Partial of r with respect to y is 0, 1, minus 4. So the cross product rx cross ry is 1, 0, minus 3, 0, 1, minus 4 equal to, so 3 in the x component, it's this cross product, right, 0 plus 3. And then in the j component, it's 0 plus 4. And then in the k component, it's 1. 3, 4, 1. So this is equal to double integral over r. One more ingredient. The curl of f defined along r of x, y, right? So the curl of f was z, x, y. Z is equal to 12 minus 3x minus 4y. So that's z, x, y. X is x, is y is y. I forgot the minus 2. All right, that's z equals 12 minus 3x minus 4y. So all that times minus 2. So now we've got all our ingredients. So minus 2, 12 minus 3x minus 4y, x, y, dot, that cross product, 3, 4, 1, dA. All right, so let's evaluate that cross product, or dot product. So double integral over r, so I have minus 6 times this. And then minus 8 times x. And then minus 2 times y, which is the double integral over r. Let's factor out the negative there. So 6 times 12 is 72. And then I have got 18x plus 8x. And then I've got 24y plus 2y dA. All right, so minus all of that. No, wait a minute. Oh, these are plus. No. Let's not do it that way. So minus 72. And then it's going to be plus 3x, plus 18x, minus 8x. Right, so that's 10x. Minus 18x, no, plus 18x, minus 8x. And then plus 24y, minus 2y. There we go. dA. So this is equal to, and what was r? The description of r is right here. X goes from 0 to 4, and then 0 to minus 3/4 x plus 3. So 3 minus 3/4 x, and then 0 to 4. So that is 10x plus 22y minus 72 dA. So antiderivative with respect to y, we have 10x minus 72y plus 11y squared from 0 to 3 minus 3/4 x dx. Oh, this was dy dx, which is equal to so 10x minus 72 times 3 minus 3/4 x minus 0 plus 11 times 3 minus 3/4 x quantity squared. So we could factor out here a 2. Well, that won't be enough to cancel that out, will it? Let's see, let's factor out 3 minus 3/4 x. So now we have 10x minus 72 plus 11 times 3 minus 3/4 x. So this is equal to so I have 10x minus 3/4 x, so that's 40/4 minus 3. So 37/4 x minus 72 plus 33. So 9 and 6, so 39 dx. Almost there. So integral from 0 to 4. So 3 times 39, so 90 plus 27, minus 117. Let me feed that into Mathematica. So this is equal to 117x minus 57 or plus 57 over 2 x squared minus 111 over 48 x to the 4th from 0 to 4. So minus 117 times 4 plus 57 over 2 times 16 minus 111 over 48 times 64, which, after all the arithmetic comes out to be minus 160. Okay, so at this point, it would be interesting, so that's the calculation there. It would be interesting to actually calculate this line integral directly. It's going to take a lot of work because there's 3 parts. There's the bottom part, this bottom curve here, this curve here, this line going up, this line going down. So you'd have to do 3 separate parameterizations and plug those into this vector field and then calculate that line integral. I'll tell you what, I'm going to pause the video now and actually do that calculation for you so that we have it written down. Okay, so there was a little glitch here. This is a 7. I had something else there before. I had 33 or something, but this is a 7 here. And then you calculate the integral and get minus 220. So now we're going to directly calculate the line integral and compare. Okay, so we forget about the surface entirely. We're just doing the line integral in 3 dimensions. And we've got these 3 pieces, this side, this side, this side. And then we use these standard parameterizations for the line, R1 of t equals 4 minus 4t, comma 3t, comma 0, where, this slope vector is minus 4, 3, 0. So R1 prime is that slope, and t goes from 0 to 1. R2t, R3t, same idea. Base point plus slope vector, derivative is the slope vector. And then this is f, x plus y squared, comma y plus z squared, comma z plus x squared. So f of r1 of t is equal to, right, this is x, 4 minus 4t, plus y squared is 9t squared. So 4 minus 4t plus 9t squared. Y plus z squared is 3t. Z plus x squared is 0 plus 4 minus 4t squared. So that's f of r1, f of r2, f of r3. So the line integral of f dot ds over c, where c is this triangle, right, is a line integral over c1 plus over c2 plus over c3, where you have these three parameterizations for those three sides. So that's the integral from 0 to 1. F of r1 of t dot r1 prime of t dt. Right, that's the definition of the line, the vector line integral. F of r dot r prime dt from a to b for t, 0, which is 0 to 1 for all three. So grabbing those, so those compositions, we calculated those here. The derivatives are right here. So we're sticking all those guys in there. So this is f of r1 dot r1 prime, f of r2 dot r2 prime, f of r3 dot r3 prime, adding up all those three guys. So we get this business here, which when you collect like terms, you get this right here, integral from 0 to 1, which is minus 169 plus 338 over 2 minus 660 over 3, which is minus 220. Right? So the same answer, as it should be, because that's what Stokes' theorem is telling us. Okay. Let's take a slightly different kind of example. So let's calculate f dot ds over curve C, where f is equal to y plus sine x, comma, z squared plus cosine y, comma, x to the third. And r of t and c is given by r of t equal to sine t cosine t sine 2t. Okay, let's use Stokes' theorem to calculate this. We could do it directly, right? This could be calculated directly, but you see what the problem is going to be is you're going to start having that f of r of t is going to have like, so x is sine t, so you're going to, and y is cosine t. So what's this going to be? That's going to be like cosine t plus sine of sine t. I mean, it's going to be pretty bad, right, when you calculate f of r of t, because you're going to have these sine of sine t things here. And then this is going to be what? Like z squared, so that's sine squared 2t plus cosine y, which is cosine of t. It's going to be pretty messy, right? But if you calculate the curl of f, it might simplify because you're taking derivatives. So let's give that a go. Okay, let's use. Notice I didn't mention a surface. So let's use Stokes' theorem to calculate. Okay, where the surface is z equal to, well, we need that this boundary curve lives on the surface. The boundary curve lives on the surface. So sine 2t, z, it's supposed to be on the boundary, sine 2t, right, which is 2 sine t cosine t, which is 2xy, where the surface is z equal to 2xy. Right, so it's got one of those surfaces again defined by a function z equals f of x, y, and this is actually a saddle type surface. It's not the usual one. It's got a slightly different orientation, but it's going to be a saddle surface. So that's an example of a saddle surface right there. It's got a simpler equation than before, but it's not oriented with regard to x and y in the way we've talked about it before. Okay, and then what's the region in the xy plane that we're using? The surface is this, and then this, which is parameterized as r, x, y, again using the trivial parameterization. X is x, y is y, and z is 2xy. Over the region r, which is just equal to what? It's just equal to the unit disk. Why? What's this boundary curve for the surface? It's sine t cosine t sine 2t. R of t is sine t cosine t, and then z is sine 2t, so x squared plus y squared equals 1. Forgetting about z for the moment. X squared plus y squared equals 1, so we're just over the unit circle here. Right? It's the set of all x squared plus y squared less than or equal to 1. Okay, let's go over that setup again real quick. Calculate f dot ds, this line integral, where this is f, and c is this. Okay, so I'm not given a surface at all. But, I can make a surface that has this boundary curve, in which case I can apply Stokes' theorem. Okay, which surface should I choose? Well, anything that works. This is the boundary curve of the surface. So z, which is sine 2t, which is 2 sine t cosine t, which is just 2 times xy, will work just fine. Because it satisfies this, or well, this satisfies that equation, so this boundary curve lives on that surface. Okay, and then we're just restricting the part of the surface, which is within this x squared plus y squared equal to 1 circle. Because on the boundary curve, x squared plus y squared equals 1, and then the z is moving up and down. Okay, but the x and y are restricted like that. Okay, so let's get all our ingredients together. So f was equal to this. All right, so we've got f. So now we need the curl of f, and hopefully that'll simplify. So I, j, k, partial x, partial y, partial z, y plus sine x, z squared plus cosine y, x to the third, is equal to, so in the x component, 0 to z. Looking better already, right? 0 and then 2z. In the j component, it's going to be this product, which is 0 minus 3x squared. Oh, I think it was minus 2z. Right, minus 2z. Right, 0 minus 2z. This one is 0 minus 3x squared. And then in the k component, this is 0 minus 1. So that's the curl, right, which is definitely a little bit easier looking than this. Okay, and then the parameterization of the surface was equal to xy to xy. So partial derivatives are x, 1, 0 to y, ry, 0, 1 to x. And then which cross product are we using? Which way do we need to orient that surface? Well, the boundary curve C, right, because x is cosine t, y is sine t, right, x is, oh sorry, x is, it's the other way around. So x is sine t, y is cosine t. So at t equal to 0, we are here. At t equal to pi over 2, we're here. Yeah. So it's oriented in the clockwise direction. Oriented in the clockwise direction. So now, this is x, this is y. Right? If we drew a picture of that surface, right? So here's the boundary curve, and it's in the counterclockwise direction. X, y. So whatever that curve is doing exactly, it's kind of like a circle bobbing up and down twice. Boom, 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 boom. Doing like that. And it's going in this direction. Right? When you view it from above, it's going in the clockwise direction. So if you're going to be sliding your right hand with your fingers in that direction, right, in the clockwise direction, your thumb is pointing down. Thumb pointing down. So S is pointing down. Right? Because the right hand isn't going counterclockwise, it's going clockwise. So we don't want Rx cross Ry. We want Ry, which is in this direction, cross Rx, which is in that direction. So Rx cross Ry is going to be equal to Yjk, I'm so used to writing it the other way. Ry cross Rx, 0, 1 to x, 1, 0 to y. So this is equal to 2y, 2x, and then k minus 1. Okay, so there's f. There's curl of f. There's rxy. This is ry cross rx. One more ingredient, the curl of f along r of xy was equal to what? Well, x is x, y is y, and z is 2xy. So this is minus 2 times 2xy. X is x, y is y. Minus 1 is minus 1. So this is equal to minus 4xy minus 3x squared minus 1. Okay? So the line integral over C of f dot ds is equal to, and this is Stokes' theorem, right? Double integral over the oriented surface, curl of f dot ds, which is equal to, by the definition of, the vector flux, so curl of f dot dr, which is curl of f r of x, let me write out the whole thing, over r, curl of f along rxy dot ry cross rx, instead of rx cross ry in this case, dA. So that's that double integral definition. So this is double integral over r, and this vector field is minus 4xy minus 3x squared minus 1 dot 2y, 2x, and 1 minus 1 dA. So it's equal to double integral over r minus 8xy squared plus 6x to the third, or minus 6x to the third, 4 times 2, minus 6x to the third plus 1 dA, where r, remember r is the unit circle. Right? So since we're working with the unit circle here, probably we want to go to polar coordinates. Okay, so this is, so let me rewrite this a little bit so it'll be easier to transform to polar, or 0 less than r less than 1, 0 less than theta less than 2 pi. Right, so that's the region r. So double integral over r. So we got some x squared and y squared stuff. So I'm going to factor out minus 2x. And then I'm going to be left with 4y squared plus 3x squared plus 1 dA. So that's going to be equal to double integral over r minus 2x, and then I've got y squared plus 3x squared plus y squared plus 1 dA. So this is equal to the integral from uh, 0 to 1 for r and 0 to 2 pi for theta. So minus 2x minus 2r cosine theta. Y squared is r squared sine squared theta plus 3r squared plus 1 outside here, and then r dr d theta, where that r is multiplied by everything in here. Right, so this is equal to double integral to 0 to 1 for r, 0 to 2 pi for theta, multiplying through by r, minus 2r squared cosine of theta, times r squared sine squared theta plus 3r squared plus r dr d theta. Factor an r squared out of here. So I have minus 2 r to the fourth cosine of theta sine squared of theta plus 3 plus r dr d theta. So antiderivative with respect to r, so all this in here is just constants. So I have minus 2 sine squared theta plus 3 times cosine theta. And then here's the r to the fourth, 1/5 r to the fifth, plus 1/2 r squared from 0 to 1 d theta. So this is equal to the integral from 0 to 2 pi minus 2/5 sine squared theta plus 3 times cosine theta over 5 plus, then this is just a half d theta. All right. So now to solve this, I'm going to let u, well, this one is going to be just pi minus 2/5 sine squared theta plus 3 times cosine of theta and d theta plus this integral is just going to be pi. Just get this one out of the way. Now I'm going to let u equal sine theta. So du over cosine theta is d theta. So this becomes the integral from u equals 0 to u equals 2 pi minus 2/5 u squared plus 3 du plus pi. So it's equal to integral from u equals 0 to u equals 2 pi minus 2/5 u squared minus 6/5 du plus pi. So that's equal to minus 2 over 15 u to the third minus 6/5 u from u equals 0 to u equals 2 pi plus pi. U was sine theta. Sine theta from, or not u equals, but theta equals. Theta equals. Theta equals. Theta equals. So this is from theta goes from 0 to 2 pi plus pi, but these are all just 0 because sine at 2 pi and at 0 are both 0. So the whole thing just turns out to be pi. Oops, I'm getting pi squared. No, it's pi. How did I get pi squared here? Yeah, just pi. Okay. So that's the answer to that question. So that is all for the lecture on this section.